Hi, in this video, we want to take a look at post hoc analysis. All right, so we're in the situation where we've done an ANOVA test, or maybe a Kruskal-Wallis test, or possibly chi-square test with binomial distributions. And we want to check to see, okay, where are the differences? So remember, when I run ANOVA, I'm checking to see, is there one or more difference in the averages between different subgroups? All right, so I conclude that there's one or more differences going in there. So now I need to know which ones. Now, there's some problems that are going to come up. Remember that whole type 1 error and type 2 error stuff that we were talking about? Well, think about running a test, and then running another test, and then running another test, and running another test. Every time I run a hypothesis test, there's a chance I make a type 1 error. There's a chance I make a type 2 error. Now, as statisticians, we always worry about the type 1 error and don't really worry about the type 2 error nearly as much. So, we have this lopsided view on hypothesis testing in this situation. And if you think about doing test after test after test for all these different hypothesis tests, the chance of me making one or more type 1 errors is going to increase as I do more and more tests. And so what we want to do when we do our post hoc analysis, we want to go in and make modifications so that I'm not increasing the risk of making a type 1 error. All right, so post hoc analysis is the analysis that we're going to be doing after we've reached the conclusion that we need to dig in deeper. So we have this Latin for after this. In statistics, post hoc analysis often refers to looking at the data after an experiment was performed to identify patterns or differences that were not specified a priori. Now, the multiple comparisons problem is that when I run more tests, there's more opportunities for a mistake. So the probability of not making a mistake goes down. And so we're going to need to make an adjustment on some things. And so, specifically, we're going to worry about the type 1 error risk more than the type 2 error. So the more tests I make, the more opportunities I have for type 1 error, which means the probability of making one or more type 1 errors increases as I do more tests. All right, so that is to say, we don't want to reject the null hypothesis if the null hypothesis is correct. All right, so let's take a look at a visualization of the probability of making a type 1 error, one or more of them, when I set the alpha value to 0.05 for each individual test. So I'm in a situation, I'm going to make multiple hypothesis tests, and for each individual one, I'm going to reject the null hypothesis if I see a p-value less than 0.05. All right, so very standard. Now, and with my first test, there's a 0.95 chance that I'm going to make the right call, in terms of type 1 error. And then second time, 0.95, then 0.95, 0.95. It's going to work out that the probability of not making any type 1 errors is going to be 0.95 to the power of n, okay? And so you can see that what's going to happen, this is going to be 1 minus that 0.95 to the power of n, and you can see that the probability of not making any type 1 errors, this is the probability of making a type 1 error, probability of making a type 1 error increases to nearly 1 with more tests. And so this is not what we want as statisticians. All right, so that family-wise error rate that I referred to a moment ago, this is the probability of making one or more type 1 errors. All right, and you can see that for large values of n, for any non-zero alpha, this is going to be really close to 1. Right? Even if I have a really, really small alpha, this will go to 1 for enough tests. We'll never actually reach 1, but we're really, really close. All right, so we have a couple of different corrections. The two that are most common are Tukey's honest significance difference and Bonferroni correction. All right, so Tukey's honest significant difference test also abbreviated HSD, is a single-step multiple comparison procedure and statistical test. It can be used to find means that are significantly different from each other following an ANOVA test. And so to run this, we're going to use the multcomp package in R. And here we're just using the MT-CARS datasets. Once again, calling that. And we're just running ANOVA, miles per gallon, depends on the number of cylinders. And so here, when I run this, when I run my test after the ANOVA, what I'm going to do, I'm going to compare the different number of cylinders and the miles per gallon's averages. And so I'm going to compare 4 cylinders to 6, 4 cylinders to 8, 6 cylinders to 8 cylinders. And that's represented here. And so for each one of these, I have a chance of making a type 1 error on their own. So if I was just to go individually at 0.05 as my significance level, then like I'll actually have a greater risk of making one or more type 1 errors than 0.05. And so what this function does for us is that it makes the p-value adjustment for us automatically. So that way I can reach a conclusion without having to worry about it. Like I just say, hey, make the adjustment for me and run it, and I don't need to worry about this. It adjusts the p-values for us automatically. Now, the Bonferroni correction is another way of making an adjustment for the individual test alpha value. Now, the Bonferroni correction is by far the most well-known and the most common, but it is really, really conservative to a point where it really is not feasible for a larger number of tests. But it's by far the easiest one to explain. And so what we're going to do, basically, whatever alpha value I want overall, for individual tests, I divide the alpha value that I want overall by the number of tests, and that gives me the individual alpha value for individual tests to reject the null hypothesis. Now, something I want to emphasize is that this is mathematically simple, so this is why it gets presented in every time that this topic is ever talked about. Bonferroni correction comes up because it's so simple to talk about, but it is over conservative, and so you're going to end up being very prone to failing to reject the null hypothesis, and which like we don't want to make it an error in either direction. We don't want to make a type 2 error also. So this kind of we're very, very prone to going with the null hypothesis on this. Now, where does this correction come from? Now, you can use Boole's inequality to get this. It's a very nice one-line proof in Wikipedia if you want to look at it. I chose to use the binomial theorem one and I like that more because it's a little bit less mathy, because there's plenty of like high school algebra courses that will go over the binomial theorem, or pre-calculus college algebra that will go over the binomial theorem. And so I think this is a more accessible presentation to it. So if we take the family-wise error rate, take the formula we just had, I recognize that this is a binomial. So let's go ahead and use the binomial theorem. Let's expand out that summation. And now I'm going to distribute that negative sign. Now when I do that, the negative ones cancels with the 1. This becomes a positive, and then I have these other terms here that have higher powers of a relatively small value of alpha. All right, and so that means that if I dropped all of these off of here, notice that I will have an alternating sign aspect going on, but overall all these terms all together will be negative. And so if I drop them, I'll get something greater than or equal to the family-wise error rate. And so here we can see that the family-wise error rate is always going to be less than or equal to n times alpha. And so, and remember, alpha is the individual test, type 1 error risk tolerance that we have. And so I know that if I take the individual test value, multiply by the number of test I'm going to run, I'm going to get something greater than the family-wise error rate. So then what do? We just divide by n. Could not be simpler, could not be easier for us to do this. Now, if we want to run this in R, when we run our hypothesis test, we're going to get p-values returned back to us. And what we can do, we can use the p.adjust function to automatically make adjustments for us. And so here, after I have the p-values that are the output of a hypothesis test, I put them into the function, I specify the method, and it will automatically make the adjustment for the p-values for me. And so then I can make my decision where I don't have to worry so much about the risk. Now, the Bonferroni correction is overly conservative. So it is reasonable for us to use other methods. And all these have advantages and disadvantages. Here are the ones that are in base R p-adjust options. So we have Holmes method. It's simple, powerful method that controls for family-wise error rates. The Hochberg method is a setup method controlling the family-wise error rate. It is more powerful than Holmes method under certain conditions. Hammel's method is a generalization of Holmes method, and Hochberg's method is more powerful than both, but it's more complicated. But good thing for us, we can just let R do all that complicated stuff. Now, Bonferroni, this method controls a family-wise error rate, but it's very conservative if we're doing a lot of tests. Now, the Benjamini and Hochberg method controls the false discovery rate, FDR, the expected proportion of false discoveries among the rejected hypotheses. It's less conservative than Bonferroni's method. And then Benjamini and I don't know how to say that method, also controls the false discovery rate, but it's more conservative than the BH method, particularly for small values, for a small number of tests, and when there's a large number of comparisons. And then FDR, this is the same as the BH method, and also the function will take the modification of none, meaning that it just takes the straight value and doesn't adjust the p-values for you, which we need sometimes in statistical programming. All right, so here let's go ahead and just take some values. So let's say these are our p-values that we have, and we're going to make adjustments with each of these. And notice first one is none. Then we have all these other ones that we talked about previously. I'm going to use the sapply function to quickly, in one shot, get all of these. And so now I have a data frame. So here's the original p-value. And so you can see that across the board, the p-value increases from the original. So here I have 0.01. All of these are greater than 0.01. Here is 0.03. Here is, everything is greater than 0.03. 0.04, everything is greater than 0.04. Here, that's not too much of a difference though. 0.07, and now here we can see that we actually got the same values. Now, something that's important to realize, when we drop this in, these are taking into consideration all four of these at the same time. And so if I was to tack on a few more p-values, it would make it, the numbers would be slightly different for these p-values. Now, something that I feel very important for hypothesis testing is making visualizations to convince our audience. So one thing that we can do is, to make sure that things are right, is visualize what's up. And also, at times, we can actually skip doing some hypotheses tests if we just have subject matter knowledge that, hey, I don't even want to check this. I know they're different, or I know they're not different. Therefore, I'm going to skip over certain pairs. By skipping over some of them, what this can do for us is that we have fewer hypotheses tests going. Therefore, we have less risk of a type 1 error. Skip tests that you don't need to make. All right, so the first way to visualize your results for your post-ANOVA test is going to be just using bar plots of averages. I find that this is a good choice for when we have stakeholders that have a weaker math background. Bar plots are easy geometry to interpret, put the number on there, and usually things go pretty well. Now, a disadvantage of this is that we don't know about sample size and we don't know about sample variance when we present this. But if I have stakeholders with a weaker math background, well, this is probably all that they're going to want to dig their teeth into. Now, the next one is going to be a B-swarm plot. These aren't as common as other methods, but what we're doing is that for each of the predictor or each of the factor levels, the group levels, I just put the dots, dot plots for their values, and visually we can see the difference between each of the groups pretty easily. I feel like this works with just a little bit more data, like maybe double would be nice, but I find that these are a good choice for people who aren't comfortable with math when you need to be able to talk about variance considerations and sample size considerations. Because you just say each individual one corresponds to a record, subject matter experts are going to adhere to that. They're going to understand it very easily when you say one dot is one record. Now, box plots. Box plots are a 5-number summary of our data. Super easy if you're willing to look at it. A lot of people don't feel comfortable with box plots, so I tend to not use them. My last attempt to use them at work actually failed miserably, and I thought I explained it pretty well, but when I looked at faces, like, no, they weren't getting it. So use these with caution. Typically, I find it's best to lead in with the bar plots showing the mean or median first, then go to here to show the variance. The presentation I was referring to, variance was a big deal, and my project resulted in a huge reduction in variance. And to show it, I was trying to use box plots. And so box plots, we're going to need some more data to use these. So we want probably at least 30 in each subgroup to start using box plots most of the time. Think about if I only had 5 data points in a group and I do a box plot. Well, a box plot is a 5-number summary. There's no point in using a box plot for that. All right, so here let's run through some examples of post-hoc analysis. So I'm going to run ANOVA. I conclude that there is a statistical difference. And then I'm going to run pairwise.t-test. So after ANOVA, I run pairwise t-test to go through. Now, in real life, if I have subject matter knowledge that tells me that certain pairs are equal to each other or different than each other, I'm not even going to worry about those. I'm not going to look at those. I might just manually skip over the pairwise stuff. The pairwise t-test puts everything in this weird format. So 4, 6, and 8 are the levels of the cylinders. And you'll notice I've got 2 rows. So there's 3 levels, but it ends up being a 2x2 table. And this is a way to store the results in a more compact manner using less memory. Oh, and we can adjust the p-value automatically by just specifying a parameter. This invokes that p.adjust function for us. Now, another option we have when we have the Kruskal-Wallis test, we can use the pairwise Wilcoxon signed rank test. And so here, I conclude that there's a statistical difference between the subgroups using the Kruskal-Wallis test. So I know that there's a difference among different subgroups. I don't know what the differences are. And so we're going to use the pairwise Wilcoxon signed rank test to achieve that. And when we see, we get a similar output here. Oh, that should be chi-squared. I mean, I changed something previously. All right, so now what we can do, we can run a chi-square test on categorical data. So let's say I'm in a binomial situation. I have group 1 and I have success failure, group 2 success failure, group 3 success failure. And so here, each group is the number of cylinders, and then success failure, it corresponds to it being an automatic transmission or a manual transmission. And so we have binomial data for each subgroup. I can run a chi-square test. I conclude that there's a difference somewhere by the chi-square test. Now, the chi-squared test isn't tuned for this. This is not the best approach possible, but this is, the simplest way. This is how this is easy to understand. A lot of stakeholders who have taken introductory statistics in college are at least passingly familiar with the chi-squared test. And so it's a good choice to use. And so after that, I can use the pairwise proportions test to check to see where the differences are. And so it's pairwise.prop.test. This uses the normal distribution to approximate the binomial distribution. Now, something that you'll notice is that this concludes at the 0.05 significance level. This concludes that 4 and 6 are equal proportions. Now, with this p-value, this concludes that 6 and 8 have equal proportions, but 4 and 8 do not. So notice that this hypothesis test says that the proportion for 4 and 6 are the same, that the proportions for 6 and 8 are the same, but it says that the proportions for 4 and 8 are not. And so we can get this conundrum going, and this paradox. So just be aware of this. This can happen. If I have more data, typically this won't be a problem. If I have a large amount of data for each subgroup, I typically won't have this headache. All right. Well, I hope you enjoyed this. Life is short. Do math.